Broadcast is now starting. All attendees are in listen-only mode.
Hi everyone, welcome into today's webinar. This is Stacy at rheosense. I hope that everyone is doing well, and as always, we thank you for joining us. We appreciate your support. Today's webinar is going to be a continuation of a theme that we initiated a few months ago, and that was to start to go over again fundamentals behind rheology and rheology measurements. The reason we wanted to do this was because we were finding that many of our customers and potential customers weren't formally trained rheologists, but rather had very broad backgrounds. And we thought that it would be helpful to start going over all the basics again to help the customers out so that they can make the most of their experiments and such. So today's topic is following along that theme that we initiated a few months ago. And as you probably know, one of the challenges when you're moving into a new scientific specialty is the language. If you've been in it for a while, then you get it. If not, then it can be kind of difficult because the language has oftentimes been built up over decades, if not even longer. So today's topic then is we want to talk about the idea of that there's not a single viscosity. You'd think that would be the easiest thing to do and the best way to go, but no, in fact, there are many types of viscosities. Generally, they'll have another descriptor with that term, and they're used in different contexts. So what we wanted to do is go over why they exist, and what do they mean, and when are they appropriate to use. So I assure you there's a rationale for the existence of them all. They didn't just emerge from the mist. So that's what we're going to do today is we're going to go over some of the different types of viscosity. And it's not going to be a fully comprehensive list, but I think it's going to be a lot of the common ones that our customers might encounter and have actually asked us about. And there are some more advanced types of testing that I won't get into, but I think this is a good place to start and get people to understand why there's not one viscosity, but actually many. Okay, so the way I want to do this is I want to introduce the types of viscosity that I'm going to elaborate on, and I've broken them into categories because there's different reasons why there are different viscosities. So why are there different viscosities? So the first reason that we have to have different types of viscosity are that there are various types of deformation that you can apply to the sample. So if you remember what rheological properties are in general, they're characterizing a stress response to some type of deformation. And that specific property is defined by the proportionality of the stress to the deformation. And generally, viscosity comes into play when we're talking about continuous deformations or flow fields, as opposed to a finite strain. And of course, there are different types of flow fields that you can apply. So this is one reason why we have different types of viscosity, is it's reflecting the fact that we're looking at the response, the stress response to a different type of flow field. So probably the most common one that people are familiar with, and this is what most of our instruments will provide for you. We do have the extensional, which I'll get to in a moment, but this is probably the most common one, and it's the most common one that people use our instruments for, and that's the steady shear viscosity. And generally, these are the common notations for that type of viscosity. The other possibility that another common flow field, and we also have instrumentation that will provide this type of flow field, is an extensional or elongational flow field. And so there's a corresponding viscosity associated with this. And it's important to realize that you need to define the different viscosities for the different flow fields because materials will respond differently to these different flow fields. So the behavior of a material under steady shear is generally very different than it is under an elongational or extensional shear. And then the final one that we'll talk about is quite a bit different, and actually our instrumentation doesn't measure this type of flow. But I did want to bring it up because it's kind of interesting in how it can relate to steady shear, even though it's quite different. And this is an oscillatory shear flow field. And the property that I wanted to introduce to you here is the complex viscosity. There's actually a number of parameters that come out from an oscillatory shear flow. It's quite a great experiment and gives a lot of information, but I'm really going to not get too bogged down in all the details. It could take too long. So I just kind of wanted to emphasize that we would have, we could discuss the complex viscosity and more specifically its relation to the steady shear. So this is one reason why we have different viscosities, is that we have the ability to apply a different deformation, and we will have a different response of the material to that deformation. So we have to categorize those properties. The second reason that we tend to have different labels for viscosities is that one of the common experiments that people do is they look at viscosity as a function of concentration or volume fraction of their colloidal particles, their macromolecules, whether it's a polymer or a protein or antibody. They look at these relationships, the viscosity versus concentration or volume fraction, and they want to model this in some way and fit equations to this data. And as a result of this process, certain scaled values fall out, and they've been over time assigned particular names. So this is another way that these many different types of viscosities have come about. It's basically scaled values that pop out from the model fitting that are very common, and oftentimes the data is rescaled in this way because it facilitates the model fits. So what we're going to talk about then is there are models that people use to fit dilute solutions, semi-dilute, which is mid-range concentration, and then models where people try to fit and handle and predict the viscosity versus concentration over the full range. And all of these are kind of similar and have some overlap. And what we're going to see is a lot of the scaled viscosity parameters that come from this type of process are the relative viscosity, specific viscosity, reduced viscosity, inherent viscosity, and intrinsic viscosity. So we're going to identify these and clarify what they are and when they're used and what they mean. And, just to point out now, another reason, just to be clear as to why we wanted to do this type of webinar, is we've had some customers or potential customers who somewhere got misled along the way, thinking that not realizing that these are all actually calculated from the steady shear viscosity. They didn't realize that you didn't need a special type of instrumentation to get these values. You just needed to be able to measure steady shear viscosity and know certain things about your sample, like the concentration or volume fraction, and then you could calculate them. So the final couple of categories, these are smaller categories, so I put them on the same slide here. So the third one is what I'll refer to as limiting values. So over time, it's become clear that many fluids, polymer solutions, dispersions, and the like, will show similar trends in the viscosity, steady shear viscosity, as a function of shear rate. And what they've seen is that they have these limiting values, these Newtonian plateaus that exist early on in the experiment at the lower rates, and then a plateau again at the higher rates, a Newtonian plateau again at the higher rates. And in between is shear thinning or non-Newtonian region. And so they've labeled these as well as the low or zero shear plateau and the high or infinite shear plateau. And this will become more clear when we look at some data and discuss this moving forward. And I think that there's a misconception about the zero shear plateau, that you have to be at zero shear rate to get this value. But this is not true, and what we'll see is this plateau, the existence of this plateau, is very dependent on the sample and can actually extend to very high shear rates depending on what you're working with. And then the final one that we'll talk about is actually, I only have one in this category, and that's the kinematic viscosity. And it sort of emerges for in a couple of ways here. One is related to experiment. So when you're dealing with specific driving force, so a specific driving force to induce the flow. And for the kinematic, that's a gravity-driven flow. It sort of emerges as the appropriate quantity when you're doing the calculation. And so an example of a gravity-driven flow where kinematic viscosity is generally measured is the old style Ubelodi or capillary tubes. It also has relevance, and this is, may not be clear to people who aren't familiar with transport theory, but it sort of arises when you're dealing with the conservation of momentum equations. And it's generally defined as momentum diffusivity, so it's quite analogous to thermal diffusivity or mass diffusivity. And it also emerges when the momentum conservation equations are non-dimensionalized and dimensionless groups fall out, one of these being the Reynolds number, and the kinematic viscosity appears in the Reynolds number as well. So it has experimental relevance, but then two, if you're trying to do fluid mechanics, essentially, it pops up and has meaning there as well. So we'll start with the first one, and this is probably the most common. And if someone says we're measuring viscosity, or presents viscosity data, it's probably this one because this is the most common. So this is the steady shear. Sometimes it is called dynamic or absolute viscosity. These are all synonymous. I put dynamic in italics because that, although people do use that term for this type of viscosity, unfortunately in rheology there's a little bit of overlap because dynamic is also used associated with the oscillatory type flow. So when people talk about oscillatory experiments, sometimes they refer to them as dynamic rheology experiments. So be careful when you see that particular label. It's common for steady shear, but it can also mean that they're doing an oscillatory type experiment. So let's just go quickly over this. I know a lot of our customers and people who have joined our webinars before have seen us talk about this a lot, but in case you're new, it's going to be important to understand a couple things about this so that you can contrast it to specifically the elongational or extensional type viscosity. So I want to get a couple details here, even if it's repetitive for you, just so you can make that comparison when we get to the extensional. So we're just going to use the simplest flow example where we have fluid between two plates. The lower plate is stationary and we're dragging the top plate at some particular velocity, some fixed velocity. And this is going to set up a flow field within the fluid, fluid of height h. And what we do is the viscosity it's always a defined property and therefore it's always calculated. So all instrumentation, and we talked about this in one of the previous webinars, involves a calculation for the viscosity. In other words, no instrumentation directly measures viscosity. It is always calculated, and it's generally a multi-step process that's specific to the instrumentation. So as we talked briefly at the very intro there, it's a proportionality between shear stress and, in this case, shear rate, which is the appropriate way of quantifying the deformation in a steady shear flow. And so what is that shear rate for this simple flow configuration? And I'll just take an opportunity to do some repeating of some of our previous content. And the idea behind rheology instrumentation is that because you're often studying very complex fluids, you want to set up as simple a flow field as possible. So rheometers are designed to have simple flow fields to facilitate the calculation of the rheological properties. And so this is probably the most simple one. And it's probably the best to illustrate. So the shear rate, what is that in this particular flow channel? This is defined as the velocity gradient perpendicular to the direction of flow. So what happens when we are shearing the fluid by moving the upper plate is that we set up this velocity profile. And what we see is the velocity is only non-zero in the x direction, and it varies only in the y direction. And so we have a gradient in the velocity in the y direction, which is the direction perpendicular to flow. And that's how we define the shear rate. And it's very simple to calculate for this type of flow field, and it's in fact a constant. It's just the velocity of the upper plate divided by the fluid gap height. And the shear stress then, shear stress is just force per unit area. So what is the force per unit area on the plate as we're dragging it along? So this is how we calculate viscosity. And to sort of better understand what type of motion you're imparting onto the fluid here, if you just look at the flow field that's described by the arrows. So the arrows, the length of the arrow is reflective of the magnitude of the viscosity at that particular position throughout the fluid. So 0 down here at the stationary plate, and then max value up at the plates that is moving. So what's happening when you do this type of shear motion is you're basically, because the gradient is perpendicular to flow, the adjacent fluid elements are being forced to move, essentially slide past each other, because they're moving at a different velocity. And that's often why that people think of this particular property as being reflective of some sort of molecular friction. And I'll take the moment here to repeat things I always say, that it's a great parameter if you want to understand your materials, because it really does reflect what's happening on the molecular level, both the individual components and then how they interact and how they structure due to these interactions. And of course, you can have viscosity is not necessarily going to be Newtonian or independent of shear rate. It can certainly, for more complex fluids, depend on shear rate and will also depend on temperature. But shear rate, looking at the dependence of this, is also quite informative, because if you remember, shear rate has dimensions of inverse time. You can clearly see that based on the equation that we have here. So velocity divided by a length scale would be inverse time. And varying shear rate is going to basically probe events on different characteristic timescales happening within your sample. So it's very informative in terms of understanding to do a full shear rate sweep. Okay, so this is steady shear, dynamic, absolute. The majority of our instrumentation measures this. You also get this from rotational instruments, cone and plate, parallel plates, cuvette, things of that sort. So while we're talking about the steady shear viscosity, I wanted to actually jump into looking at these limiting or plateau values. Since we're thinking about steady shear viscosity, let's talk about what these values are. So here's an example of this is a protein solution where we've measured steady shear viscosity as a function of shear rate. And because I wasn't able to get the entire flow curve, I used a model here to actually fit it and extend it out, just so you could get an idea of how this would look. Generally, one of the challenges in getting the full flow curve is that you oftentimes need multiple styles of instruments to get the different shear rate ranges. So, but this will serve to illustrate my point. The zero shear viscosity, or the low shear plateau viscosity, is this plateau initially prior to the onset of shear thinning, prior to this critical shear rate. And then after the shear thinning has ceased, ultimately then at high enough shear rates, you'll merge to this high shear or infinite shear plateau viscosity. And they're very different in terms of what they're telling you. So the low shear plateau is, as is clear from the plot and as makes sense when you think about what's contributing to this low shear plateau, is it's a higher value in viscosity. And it exists because there's some restorative mechanism or some mechanism acting microscopically that's acting to resist the deformation of the structure that the external flow field is imparting. So it's able to maintain some state close to, but not quite at equilibrium, because we still have an external flow field. And this mechanism is going to generate what we refer to as a thermodynamic stress. So one of these restorative mechanisms, and we've talked about this in some other webinars, is Brownian motion. So you'll see Brownian motion is important in proteins, macromolecules, colloidal particles, any objects in a particular length scale range from about 1 nanometer to 1 micron. Brownian motion will be relevant, and it'll, up to a point, up to a particular shear rate, can act to resist this deviation from the equilibrium state. But then at some point, the shear flow overpowers this mechanism, and we see the shear thinning. And then ultimately, as we get to this high shear plateau, we're very far from an equilibrium state. And when I say equilibrium state, I'm referring to the microstructure, or basically the spatial positioning of all your components in the system. And this is actually a hydrodynamically dominated state, because all of our thermodynamics are basically wiped out by the shear flow field, and what we're now looking at is predominantly hydrodynamic. And if you look at the difference between these two plateau values, it gives you an idea of the strength of thermodynamic forces. So thermodynamic forces are, as I stated, Brownian motion, but could also be electrostatics or steric repulsions in the case of, say, soft polymer layers grafted on a colloidal particle. Those would all be thermodynamic types of forces, and also reflective of the degree of structure that was formed. So that, by the degree of structure, I mean, did it have some sort of aggregated state, or did it have In the case of long-range electrostatics, particles can actually position on a lattice structure, so like a crystalline lattice structure. So the difference between these two is going to give you an idea of the strength of these thermodynamic forces and the degree of microstructure that existed because of them. And so I'll probably leave it there, although I could probably talk about it more, but I think that defines those particular types of viscosities, the plateau values that exist in many complex fluids. And I just wanted to point out that there seems to be a misconception when someone hears the term zero shear limiting viscosity, they think that they have to be at a zero shear rate. But this is not true. So as you saw on the previous slide, we were seeing the onset of shear thinning somewhere around 2,000 inverse seconds. It's not a universal range to obtain these plateaus. They're highly dependent on the sample. And so I have two examples to illustrate that point here. One of these, so in both cases, we're looking at steady shear viscosity as a function of shear rate. On the left plot, we're looking at different concentrations of xanthan gum. So xanthan gum, as you know, is a very high molecular weight polysaccharide. Generally, molecular weight is a million plus. We don't know the exact one for this particular group of samples. And on the other plot, on the right plot, we have bovine gamma globulin, which is a model protein, which has molecular weight somewhere around 160,000. And generally, these are interpreted as behaving like a colloidal system, almost like a soft particle, albeit anisotropic and non-uniform. So what I wanted to point out is that we clearly obtained the low shear plateau for our protein solutions. And this plateau varies the extent to the range over which it lasts. It varies quite a bit from sample to sample here. So we can see that in some instances it lasts up to 2,000 inverse seconds, and in other instances it lasts up to 20,000. So the onset of the shear thinning and the sort of loss of this low shear plateau is highly dependent on the sample and basically the time scale of events that is occurring on the microscopic level. So if we think about it for these proteins, we had talked a moment ago about the importance of Brownian motion acting to actually contribute to the existence of this plateau. And so if you have either primary proteins or aggregates of different size scales, then the diffusion of those will change with size. So larger objects will diffuse more slowly, and you'll see shear thinning earlier, like we do in the red curve. Smaller objects will diffuse more quickly, and shear thinning onset will be later, as we see with this gray curve. So, and then to contrast this with something with this very large molecular weight, xanthan gum, and because we don't know the exact molecular weight here, we don't know exactly what regime we're in terms of whether we're just overlapped or we have some entanglement. But in this case, I wanted to point out that although we weren't able to get a low shear plateau, if you look in literature, I got sort of an estimate of if we could have achieved the rates, then the low shear plateau would have been somewhere between 0.01 and 0.1 inverse seconds. So a few orders of magnitude lower than what we were able to obtain. But you can see that we're getting close to the high shear plateau. So the point is that these limiting plateaus they're not a universal range. So you would never say, I must operate between these particular shear rates and they must be exceptionally low. It's highly dependent on your sample and essentially the characteristic relaxation time or times that exist. Because remember, shear rate is an inverse time scale and is probing the relaxation times in the system. Okay, so now let's move on to a different type of flow field and then therefore a different type of viscosity. And although there are different ways of imposing an extensional flow, because we have a particular flow channel that applies this type of flow, I was going to use our system as an example, but I will point out that there are other means of introducing extensional flow and measuring extensional viscosity values, but I'll use our technology as an example. So our technology has what is referred to as a hyperbolic contraction and expansion. So that's what the image we have here on the right. And so fluid is flowing along the channel, and then at some point, the diameter of that channel contracts and then ultimately expands again. So what's the relevance of that? The relevance is that this contraction is going to introduce a velocity gradient that now is parallel to the direction of flow, or in the same direction as the flow field. So remember, this is different than when we talked about the steady shear, where the velocity gradient was perpendicular to the flow field. Now we've changed the geometry so that we have a velocity gradient parallel or in the same direction as the flow field. And an easy way to understand why you would have that is because if you realize that we have a consistent volumetric flow rate across our entire system, so volumetric flow rate is represented here by Q. So when we have a constriction or this contraction where the cross-sectional area A sub C is consistently going down, because we have a constant flow rate, that means the velocity has to increase as we move along, as we move into the channel. So to keep the volumetric flow rate constant, as the channel narrows, linear velocity will increase. And so that now gives us an extensional rate because we now have this non-zero velocity gradient in the direction of flow. And this is sort of the ideal increase in viscosity, or I'm sorry, increase in velocity, linear velocity as we enter the channel, and then further decrease as we exit the channel. So this is going to act then, so you can imagine, as opposed to the steady shear viscosity where we're forcing elements to slide past each other, now because we have the velocity gradient in the direction of flow, now this is going to act to stretch or elongate the fluid element. And so you can imagine that we need a new parameter here because the response of the material can be quite different to those two different types of deformation. And you can imagine that if you have a polymer coil, it could just deform slightly or rotate a bit in the shear flow. But if you really have a high extensional rate, then you could really stretch out that chain and get a very different response in terms of this viscosity. So don't get, I wanted to put up the equations just to show you consistency and how we calculate them, but don't focus too much on them. Let's just look at, we define the extensional rate as I mentioned. Basically, this is just calculated specific to the type of experiment you're doing. So this is how it's calculated for our channel with the constriction. And the form of the equation is analogous to the steady shear. It just looks a bit different. So in this case, our extensional viscosity is going to be, the stress for this system is the pressure drop across the constriction divided by this Henke strain. So that's our stress in this case. And then we divide the stress divided by our deformation rate, which is the extensional rate in this case. So the way it's calculated is analogous to the other, but now we have a different type of response and we have it due to the different type of deformation. So don't worry too much about the equations unless you want to dig into that later, but that's the general analogy there. Different type of deformation, but we're still calculating it in the same general way, stress divided by the extensional rate. Okay, so now I'm going to move into, I was unsure how exactly to proceed, because I guess maybe the most logical way of going next would be to talk about the complex viscosity, because that is another viscosity that exists because it's a different type of deformation. But that's a little more complicated, so I was going to save that till the end. Where I would sort of be forced to go over it quickly and not linger too much in the interest of time. So let's move then into thinking about all of these scaled viscosity values that pop up because people are interested in modeling or model fitting viscosity versus concentration data. So let's start with the dilute limit and see what sorts of things are going to pop up here first. So if you think, one of the common experiments people do is they look at viscosity as a function of concentration, and they're varying concentration. However, they're keeping that concentration low, because the advantage of that is that it's very simple to model this. So the way they model the viscosity in the dilute limit is to use what is referred to as a virial expansion. And that's just the language that is used. It's also used in terms of when you're doing osmotic pressure. But what it is just a power series in either concentration or effective volume fraction. And this works in the dilute limit because you can systematically introduce, higher levels of complexity by including more and more terms. So what we're looking at here, and this is where we start to see some of these scaled values pop up. So the expansion is done. So again, this is our steady shear viscosity, and I'm scaling this on the value of the solvent. So this type of experiment is done with polymers, proteins, colloidal particles, or in some instances, emulsions, anything that you can sort of treat as what we refer to as a pseudo one component system, so that you scale out the viscosity of the solvent and then look and see, and that allows you to focus the data on what's happening with these macromolecules or larger particles. So the idea is we scale out the viscosity of the solvent and treat it as a pseudo one component system. That's again the terminology that is very common in colloids, and I would argue that it's also how some people would treat the polymers. So this is where we then first define the relative viscosity. It's just viscosity of our solution or dispersion scaled on the solvent value. And the virial expansion then, as I said, is the expansion in the power series of either concentration or effective volume fraction. And concentration here is C. And now we see the emergence of the intrinsic viscosity. So the intrinsic viscosity is just the first order term in this series expansion. And if you want to think about what kind of meaning that has, because it's the first order term and we're at this limit of what we'll call infinite dilution, the average spacing between molecules is quite large. So that means that this term is not going to be impacted by the interaction of these molecules. So the intrinsic viscosity, although it's strictly defined as the prefactor to the first order term, it's very reflective of the individual molecular behavior. So things like molecular weight, intramolecular interactions. So do you have something that's a coil collapsing on itself, or is it expanded? Things of that sort. And it's actually a purely hydrodynamic effect. So you see an increase in viscosity due to the presence of these larger molecules or particles, because they disrupt the flow field, and there's an extra thermodynamic stress due to their presence. And so it's actually a purely hydrodynamic contribution. And then, of course, as we go higher in concentration, average spacing goes down, and we start seeing the importance of pair interactions, both hydrodynamic and thermodynamic. And of course, if we were to include higher order terms, which you wouldn't do in this type of analysis, you would start then looking at these higher body or multi-body interactions. So here's where we start seeing some of these scaled viscosities come out. So these sort of come from just the equations that we ultimately want to apply, and then we're defining the variables in the equation. Now some of the other scaled values come out because it really facilitates the analysis using these types of equations to extract parameters that are of interest to you. So here's an example of where we take the equations that we had on the previous page, and we're going to further do some moving around of terms and rescaling just to facilitate the analysis. So now we've taken, the first thing that we do is we take the relative viscosity and we subtract 1 from this. And this is what they define as the specific viscosity. So if you wanted to handle it this way and fit a quadratic to your data, then this would be where you would stop. However, this isn't really the ideal way to go, so you can actually further then define yet another parameter and scale it further. So now scaling the specific viscosity on the concentration, and this defines the reduced viscosity. So now the desire for this type of scaling is that when you plot the reduced viscosity as a function of concentration, now it's very easy to obtain this intrinsic viscosity parameter, again, remembering it's reflective of individual molecule behavior from the intercept, as we can see here for some model protein solution data that we have. And this then is a somewhat, I guess, more rigorous definition of the intrinsic viscosity. It's the limit as concentration goes to 0 for the reduced viscosity. So that's sort of the more rigorous way of defining intrinsic viscosity. Okay. Now, so the other thing I wanted to do in the webinar is to not only define these different types of viscosity, but show you how you could use them and how they could be of value to you. So in this case, we were looking at two different model proteins that have significantly different molecular weights. And so we can see that, in fact, the intrinsic viscosity does increase with increased molecular weight, which is what you would expect. But we could actually, so that could be valuable if you just want to have some sort of qualitative way of looking at trends in your systems. But there is also something you can do with the intrinsic viscosity to take it sort of a step further, and that's to use it to calculate hydrodynamic size or estimate hydrodynamic size. So just to quickly remind people of one way, if they wanted to get the intrinsic viscosity, this is something that you might potentially want to do with this. So the expression for the hydrodynamic radius is actually quite straightforward to get. So we just take our two expansions that we saw a couple slides ago. So we can expand it in terms of concentration, or we can do it in terms of effective volume fraction. Either way, regardless of the variable that we're using, the first order terms will have to be equal, so that the terms accounting for the infinite behavior at infinite dilution and just pure hydrodynamic disruption due to the presence of these objects, these are going to have to be equal. So if we set these equal and then find a way of relating the volume fraction to the concentration using Avogadro's number, molecular weight, and the hydrodynamic volume of the object, which is fairly straightforward to, we just assume it's spherical in this case, then we can solve for this hydrodynamic size. And so if you know the molecular weight of your particular polymer or protein, then getting the intrinsic viscosity measurement can give you an estimate of the hydrodynamic size. Alternatively, if you don't know the molecular weight, but you're able to do some complementary analytical technique like dynamic light scattering, then you could measure hydrodynamic size, you could measure intrinsic viscosity, and get some idea what the molecular weight of your polymer is. So this is where understanding what intrinsic viscosity is, how to get it, and this is just a way where it could be valuable to you if you wanted to do more than just use it as a gauge and a qualitative interpretation of samples. Okay, so this is this point of this particular slide is to illustrate another way of using the intrinsic viscosity. So this process is a little different here. Oftentimes, people would still do the dilute solution analysis and use the equations that we talked about on the previous slide to get the intrinsic viscosity as a function of molecular weight using the mark. I'm not even going to try to pronounce that and be recorded. But for my particular experiments that I was doing here, I didn't have data that was dilute enough. So what I was able to do is utilize a different model equation that exists for the mid-range concentration or the semi-dilute regime. And so this is referred to as the Minton equation. I've changed my notation a little bit here. Now my relative viscosity, I'm referring to this solvent viscosity as mu. But once I rescale everything, I still get this reduced viscosity, which we've defined earlier, which is relative minus 1 over concentration. And now we see that this is an exponential function because it's meant to handle something that's more, it's beyond infinite dilution and more into semi-dilute range. I'd probably call it semi-empirical because if you take the limit as c goes to 0, it does go to the proper equation, but then the exponential part and these additional parameters are really just introduced and shown to work empirically as comparing to experimental data. But the idea is that from fitting the model to my data, in this case I had nylon 66 in formic acid. This is my reduced viscosity as a function of concentration. So I was able to get an intrinsic viscosity value from this plot. And if you dive into the polymer handbook, it's well known that you can relate the intrinsic viscosity to molecular weight. And so we talked about a moment ago that this intrinsic viscosity, which is reflective of the individual molecular behavior, molecular weight being one of them. And this empirical relation exists. And for nylon 66 in formic acid, I was able to go to the polymer handbook and find both the prefactor and the power law exponent for this relationship. So knowing the intrinsic viscosity that I got from the data from the model fit, and getting these well-known parameters, which I got from the polymer handbook, I could get some estimate of the molecular weight of this polymer that I was measuring. So the idea with this equation is that, if you're working with a common polymer, so nylon 66 is common enough that I could find the information in the polymer handbook, but of course, there are plenty of other polymers, pages and pages of them there. So if you're working with a common polymer in a common solvent system, then you can find the prefactor and the exponent. And from those, knowing those values, your measured intrinsic viscosity value could give you an idea of what the molecular weight is. If you're working with some new type of system that you can't find the data, then of course you can generate your own master curve and then refer to that in the future as you want to analyze those types of systems again and again. So this is another way to use the intrinsic viscosity to relate it to molecular weight of a polymer. Okay, and I think we have one more scaled viscosity to touch upon. And I'm going to illustrate that one by looking at, so I talked before that people like to look at concentration dependence in dilute, and we talked about that one initially when we first defined the intrinsic viscosity. And then we just talked about how there are models that exist for the mid-range or the semi-dilute range. And then there are models that exist that are meant to work for the full range of your measurement from dilute to concentrated and even to the point of divergence. So one of these models is referred to as the Ross-Minton equation. And it's basically, it has an exponential form. So the relative viscosity is equal to the exponential of this quantity. And again, we're seeing the pop up here of the intrinsic viscosity. So just like the Martin equation, when I take the limit of this equation to go to infinite dilution, it does give me that virial expansion. So again, this is sort of a semi-empirical type equation where it does go to the proper limit at infinite dilution, but we know that it can be, by adjusting these parameters, it can be made to fit data at high concentrations. And this is actually, although it's intended to be used specifically for proteins, which is why we were using it here for our model protein gamma globulin, it's basically an analogy between an equation developed for colloidal systems. And the thought behind this is that at some point in time, you're going to add so many molecules to the system that you're going to hit maximum packing. And this is going to lead to a divergence in the viscosity. So the exact parameters that are put into the model are less straightforward than the colloidal system. So in the colloidal system, it's basically maximum packing volume fraction. Whereas here, now we're talking about, they sort of redefine it into a crowding factor, and then also what they refer to as a shape parameter, because these proteins aren't spherical, they're anisotropic in nature. So this particular equation, because of its exponential form, is going to lead to our final scaled variable. And I just wanted to point out too, I hadn't pointed this out yet, but this is, I'll do it now because I have the plot here. So hopefully I don't distract you too much, and but I wanted to make it while I had it in mind. So here I have relative viscosity as a function of concentration for, I've neglected to put my concentration here, but these are 250 mg per mil gamma globulin in a phosphate buffer at 2 different levels of sodium chloride. And relative viscosity on its own is a great way to compare data, particularly when you're changing something about the buffer. So if you think about proteins, you oftentimes adjust buffer to adjust behavior of your sample. And by behavior, I mean how the proteins are interacting. And so to truly see if you've just shifted background viscosity by adjusting your buffer, in this case by changing the level of salt, or to see if you are actually changing how the proteins are interacting, it's very important then to first look at relative viscosity as a function of concentration. Because the relative viscosity, as we've defined before, is that of the polymer or protein solution divided by the viscosity of the buffer or the solvent. So when you scale out the impact of what the background is or the solvent, now you're going to highlight what's happening with the proteins. And now if all you did was change the background viscosity of the protein, then these two curves would basically collapse on each other. And it would indicate to me that I didn't really change the interactions of the proteins. But in this case, when I scale out the viscosity of the buffer, and of course the higher concentration sodium chloride would have a higher viscosity, I see that the viscosity curve of the higher salt content buffer is still different and still higher than the other. And so this is telling me that adding this additional salt is likely introducing, some salting out of the protein, introducing some additional aggregation, and is guiding me to believe that I have changed the interactions and not just the background viscosity. Okay, so sorry for the tangent there. I wanted to point that out, that it's always very valuable when you're doing that type of comparison to look at relative viscosity as a function of concentration instead of just the unscaled value, even if you're not going to do any sort of model fit or later analysis. Okay, so the final scaled value that we want to come up with. So the Ross-Minton equation, which we just talked about, which I've sort of represented here for you, the relative viscosity having this exponential form where this is the intrinsic viscosity, which is we've defined before, and I've sort of rewritten it in a way that's more obviously analogous to the colloidal systems, although in this case I'm still using concentration, and I'm sort of considering this some maximum concentration. So it's quite common to actually use a linearized form for this equation, because oftentimes, even though you have seen an uptake in the viscosity, you're still not anywhere really near the concentration where divergence would occur. So a lot of people will use the linear form, and we get the linear form by just saying, how do we take the limit of this equation when this ratio is small? So as I stated, we're not yet close to the concentration where we see true divergence. And so this is just basically doing a Maclaurin series of this exponential, well, actually, we take the logarithm, natural logarithm at first, and then we do the expansion of this piece here that's in the exponential. And that leads us then to our final one, which is the inherent viscosity. So we take the log of the relative viscosity, and then we do the expansion and divide through by the concentration. So this log of the relative viscosity divided by the concentration defines this inherent viscosity. And oftentimes, data like I had just shown on the previous slide, instead of plotting it as is and using the Ross-Minton equation in its natural form, people will do the rescaling to inherent viscosity and use the linearized Ross-Minton equation. Excuse me. And just to point out, because I didn't bring it up before, because it's not as common as the Huygens equation, which is the virial expansion of the relative viscosity with respect to concentration. But there's an analogous equation referred to as the Kramer equation, where it's a virial expansion with respect to the log of the relative viscosity. So this also is sort of another place where the inherent viscosity pops up, and you can use this equation to do your dilute solution analysis as well. Okay, so kinematic viscosity is next. So we mentioned before when we first introduced this one kind of is the natural choice when you're doing the capillary viscosity measurement. So we have an old school capillary tube here, and this is a gravity-driven flow. And because it's gravity-driven, excuse me, density, the fluid density is going to pop up. So if you're not familiar with the way these experiments are done, what happens is you take a fluid that you know the viscosity. So if you're doing, say, aqueous polymer solutions, you would take water, for example, or if these are in some sort of buffer solution, you would take your buffer. Or if you're doing organic-based solvents, polymers and organic-based solvents, you would take your organic-based solvents. So you generally have some sort of reference fluid, and you would first measure the time that it would take for this fluid to drain through the tube. So you would get your data for the reference fluid, and presumably if it were water or an organic solvent, you would be able to find the value of the viscosity, the reference viscosity, and then the reference density. And then in order to actually get the viscosity of your sample, say your polymer in that particular solvent, then you would need to know, then you would just measure the time that it would take to drain through the tubing. And if you don't have the knowledge of the density of the, say, polymer solution, then the way this can be rearranged is we can divide the dynamic or the steady shear or absolute viscosity by the density, and this is what defines the kinematic viscosity. So kinematic viscosity is just steady shear viscosity divided by density. And so if you have no knowledge of the density of your particular solution that you're measuring, then you can get from this expression the kinematic viscosity just as a ratio of times from your sample and the reference sample, and then the knowledge of the kinematic viscosity of the reference, which should be well documented. A lot of times what people will do in this particular case is if you're doing a dilute polymer solution, say, oftentimes people will assume the density of the solution is the same as the density of the fluid. However, if you're not doing that type of experiment and you can't make that assumption, then you're going to be limited to getting essentially kinematic viscosity. So this is kind of where it's relevant to this gravity-driven flow from an experimental point of view. But this also pops up when you're dealing with transport phenomena or essentially fluid mechanics, where we're looking at conservation of momentum. So if you look at the dimensions of the kinematic viscosity, it's length squared with time. So this is a diffusivity. So this is generally referred to as the momentum diffusivity, and it's analogous to, if you're more comfortable with thinking about the thermal or mass diffusivities that exist in energy and mass balances, it serves the same role and gives the same sort of information. And then also one of the other things, and I certainly didn't want to do it for you here, but if you, one of the procedures when you're dealing with conservation of momentum in fluid mechanics is to non-dimensionalize your variables. And when you non-dimensionalize, what happens is these dimensionless groups sort of naturally pop out. And what they're used to do is, it's a very rigorous way of eliminating the unnecessary terms in the momentum balance. Because if you ever looked at, say, Navier-Stokes equations, there's this many terms, and if you're very skilled, you can go in and say which ones should be tossed out and which ones are not. But if you're not non-dimensionalizing and getting all the dimensionless parameters there so that you can actually calculate that dimensionless parameter, which is multiplying a term of order 1, it will let you rigorously and systematically eliminate terms. And so one of the dimensionless groups that pops out from the non-dimensionalization is the Reynolds number, and it includes this kinematic viscosity along with the characteristic velocity scale and then some sort of characteristic length scale. So d sub h is just hydraulic diameter. And so that's going to vary depending on the cross-section of, well, it's going to depend on the geometry of your flow configuration. So if it's a circular cross-section, then this will just translate to diameter of that circular cross-section. So, but the idea is that it's a characteristic velocity associated with the flow field and a characteristic length scale associated with the geometry divided by this momentum diffusivity. And if you're also familiar with Reynolds number indicates the transition from laminar to turbulent flow, or laminar being where you have parallel streamlines that don't cross each other, unidirectional flow. And then once you go to turbulent flow, then you start seeing basically, it's also referred to as secondary flows, because now you have, you start breaking streamlines and you no longer have the unidirectional flow. So you can have things like eddy currents and things of that sort. So low Reynolds number, we're in the laminar, and then high Reynolds number takes you to turbulent. And the kinematic viscosity is a parameter that's going to impact the transition from laminar to turbulent flow. Okay, so this will, maybe I shouldn't have saved this to last, because it's probably going to be the perhaps the most foreign to people, but I did want to bring it up because it is a common type of deformation and does define a separate type of viscosity. And there's actually sort of one final point at the very end that I want to make that can be very convenient from an experimental point of view if you have this capability. So the oscillatory shear flow, sometimes it's referred to as dynamic rheology, so oscillatory or dynamic measurements. So this is where it can be a little confusing when you realize they also use dynamic viscosity in steady shear type of test alone, but don't worry about it too much. So this is the type of flow field that we have. Now, I'll point out that we can't do this type of experiment with our instrumentation. You would need a rotational instrument. And so just as an example, I've drawn the cone and plate geometry. And what happens in this case is, instead of, so in the steady shear experiment in the cone and plate, you would just consistently rotate this upper plate at a fixed rate. There'd be some angular velocity that you consistently rotate this plate around. In the case of the oscillatory flow, what we do is we move it back and forth. So now the motion of this upper plate is going to follow a sine wave. So we're going to have some low amplitude strain. The strain is just basically related to, what is the deflection angle in each cycle that we go before we then move back the other direction. And we're going to do this at some frequency omega. So this sets up a sinusoidal strain, essentially. And just if this visual works for you, then I have an image of what this strain looks like as a function of time. So we're going to move this back and forth with some frequency. So it's going back and forth. And these experiments are generally done with this, what I refer to as a low amplitude strain. So this angular deflection, so the strain actually comes from the angular deflection divided by the cone angle, and this is going to be small. Now again, everything's relative, so small for one fluid is not small for another, so this is going to be dependent on your sample. So the beauty of these experiments really is that because it's a time-dependent strain, that means we're also applying not just a strain like you would for analysis of a solid or elastic material, but we're applying a rate of strain or shear rate because it's time dependent. So if you remember, so we can get the shear rate or rate of strain by taking the time derivative of our sinusoidal strain, and then this gives us the value or expression rather for our shear rate. So we're simultaneously straining the fluid and shearing the fluid. So this type of analysis is what you use because you're doing both to the fluid. This is how you basically quantify the viscoelasticity of a material. So a viscoelastic material is going to show both viscous type response, so it will flow, but it will also, and part of that will be basically a irreversible deformation, which is what the flow response is. But then because it has some elastic nature, there'll be some ability for the sample to recover. And so we're going to pick out both the elastic and the viscous characteristics of it with this type of flow field. So that's why it's used. And what we see is the shear rate or rate of strain is a cosine, or basically it's pi over 2 radians out of phase with the strain. So I use that language being, out of phase, because that's what happens when we start now looking at the stress response. So if you remember, all rheological properties are what kind of stress response do I get from a particular type of deformation. So now what happens is we're going to have, in general, a stress response, which will be offset by some phase angle delta. So this is sort of unknown. This is what you're going to determine. And knowing the trigonometric identities, you can take this, this stress, which is out of phase with the strain by some angle delta, and you can express it in terms of the two trigonometric functions, sine and cosine. And so that means that you can separate it into components, one being in phase with the strain and one being in phase with the rate of strain or shear rate. And so that's where we're going to get these two modulus. That's how these two modulus values are defined. So you have the elastic or storage modulus, which is characteristic of, the elasticity of the material, and that is in phase with the strain. And then you have the viscous or loss modulus, which is going to characterize the viscous nature of the material, and that is going to be in phase. This will be proportional to the cosine, so that is in phase with the rate of strain. And you can sort of see the limiting behavior here. So you can actually do oscillatory flow measurements on something that's purely elastic or something that is a Newtonian fluid, and you will get, you'll be able to measure data. It will work on both extremes, right? So what are these limits, just so you can kind of understand a little better. So when your phase angle goes to 0, that means that your stress is fully in phase with your strain and the material is purely elastic. And so we're just getting one modulus here, the viscous modulus is 0. The opposite limit, when your stress is out of phase with the strain by pi over 2, that means it's fully in phase with the shear rate or rate of strain, and your material is purely viscous. And so from the the viscous or loss modulus, you can actually get the steady shear viscosity. Because although we're oscillating here, we're setting up the same type of flow field. We're still getting that velocity gradient perpendicular to flow. So we still have shear flow. It's just that we have the oscillatory nature. But in this particular limit of a purely viscous material, then we can use the values that we get from the moduli to get a steady shear viscosity. And so the final point I want to make after all of this is there is what is referred to as a complex viscosity, which is defined as follows. It's a combination of the two moduli. And the reason I wanted to bring this up is because it's actually very interesting in terms of experimental convenience. Because it turns out that sometimes, and I've seen this happen quite a lot in polymeric systems and even in some colloidal systems, but predominantly polymeric, there are many situations where the steady shear viscosity as a function of shear rate is equivalent to this complex viscosity as a function of frequency. So if you're comparing values at equivalent rates and frequencies. And this is referred to as the Cox-Mertz rule. And the reason this is beneficial is that oftentimes it's easier to get data at low frequencies than it is to get data at low shear rates. And so when this applies, then you can often get more data at the lower frequencies, which then is equivalent to data at lower rates, without the challenges and experiments that you get when trying to go to extremely low shear rates. So it has an experimental benefit, if you will, of convenience. And it's actually, you can kind of understand, from a high level perspective, why they could have some equivalence in certain situations, because both the frequency, so frequency is inverse time, shear rate is inverse time. So changing frequency or shear rate is probing a different time scale and looking for characteristic relaxation times as you change them. The thing that doesn't always, thing that's a little different is that because we're doing a low amplitude strain, the nature of the microstructure for the steady shear experiment as you go to higher and higher rates is much more further perturbed from equilibrium than it is at the higher frequencies, because what matters so much with the oscillatory is the strain magnitude. So the fact that this happens, in some ways makes sense. In other ways, it's kind of a mystery. Okay, so anyway, I went way too long, but that's where I will end. So let me see who has held on and if we have any questions. So I'm not getting a lot of questions today, which is fine, but so I'll just give you a few more minutes in case you have something you want to ask. But let me just make the announcement that if you're interested, anyone who signed up for the webinar will get a link to be able to view the webinar at a later time and also get the actual slides. And of course, when you signed up for the webinar, you got some, you should have contact information for us. So if at a later date you think of questions that you want to ask or have any comments, then by all means, please contact us later if they weren't coming to you now. Okay, so the question, we did get a question, and the question is, can we use this Cox-Mertz rule to get viscosity at high shear rate? So I think what you mean is that can we get data at high frequencies and assume that that is equivalent to data at high shear rates? I would say that the better range to operate in with that rule is at the lower to moderate frequencies and rates. One reason for that is that when you try to go to high frequencies, you have a lot of problems with inertia in your measurements, and there's really a limit to how high in frequency you can get. So it's hard to get to high frequencies. And then also, as I mentioned before, the nature of the oscillatory experiment is that you're operating at a low amplitude strain. And so the actual microstructure, even at the higher frequencies, is less perturbed than the microstructure of a steady shear measurement at high rates. So I think that the best place to apply this rule and where I've used it is sort of lower to moderate rates and frequencies, because you have experimental challenges with high frequencies, and then also I think you would expect deviations from that difference in deviation from an equilibrium state that comes from the steady shear that's not really there in the oscillatory measurement. But it's certainly something that you can try out and see how it works. So if you have the ability to do these experiments, you can see over what range do they overlap and agree. Okay, well, I guess that was a lot of information, and so I'll let everyone process. And as I said, please do contact us if you think that you have a question later that you didn't occur to you now. And as I said before, you'll have access to the webinar in the future after the recording is processed. You'll get a message letting you know that it's ready if you'd like to view it again. And of course, you can always get all of our previous old webinars from our website as well if you are interested in some of the other fundamental discussions that we had earlier. So I guess we've gone quite long, so I'll let everyone go for today. thank you so much again for joining us. And we have webinars monthly, so we'll have another one in June. So you should get an announcement on the topic. I don't think topic or date has been finalized yet, but you'll hear about it, and hopefully you'll join us again. So take care, everyone, and have a good day.